So we are going to be talking about resonance structures. Resonance structures are important so that we can visualize the delocalization of electrons in the molecule around the atoms, so we can understand and predict how they are going to react with other atoms and predict what products are going to be made. And so when we are looking at resonance structures, some important points to keep in mind is that the sigma and pi bond electron sharing overlap. And as you can see here, the pi bond has the overlapping of the non-direct side-to-side overlap like the sigma bond has. And so that gives it the characteristic and enables it to be able to delocalize it around the atom. And therefore that results with the sigma bond. Because of that direct side-to-side overlap, we cannot delocalize any of those electrons. So similarly to pi bond electron sharing overlap, we also can delocalize any lone pair electrons as well. So moving into our first example here, I'm going to initially look at where my pi bonds are in the atom. It's like just a good starting point for me. I usually know I can delocalize some electrons about a double bond. So I'm going to break my double bond and bring it into a lone pair up here. And it is important to note that my direction of the arrow where I am moving my lone pairs. So I am breaking my bond from my pi bond and moving into its lone pair region up here on that atom. And similarly to over here, I want my arrow to go from this lone pair, and I'm going to delocalize it and move it and make a pi bond on this oxygen atom connected to this carbon atom. So, which results in this structure on the right hand side. And as you can see now, I have my delocalized pi bond made, and as well as my lone pair and my pi bond broken on this upper oxygen atom. And I am not able to do any more delocalization of electrons because that we do not have grounds to delocalize on this bottom left hand side, because as I mentioned before, we do not have a pi bond electron sharing overlap, nor a single pair of electrons to delocalize as well. And here I want to note the negative charge of on the oxygen atom and how it's being moved to this upper oxygen atom based on how we are delocalizing the electrons. So to determine formal charge in the atom is you're going to bring out your periodic table and look at what group oxygen is in, and you can see that it's in group 6 right there. And so we know that the oxygen atom wants 6 valence electrons in its outer orbital shell and its valence shell. And we are going to calculate how many it has based on what we are displaying in our Lewis structure. So we are going to count an individual electron as 1 and then a pi bond as 1 electron. So we have 1, 2, 3, 4, 5, 6, 7. So here we are displaying 7 valence electrons in its outer shell, which results in a -1 formal charge. And it's important to denote where your formal charges are moving around the molecule, because that is an important contributor to the resonance hybrid structure. So now we can start working on our resonance hybrid structure, since we have all of our electrons delocalized about the atoms in the molecule that we can. To begin building our resonance hybrid structure, I'm thinking about where exactly I delocalize those electrons. I see that it's mostly between those 2 oxygen atoms, so on this right hand side of the molecule, and therefore I'm going to represent that delocalization with a dotted line. So I'm going to start drawing my hybrid structure with a dotted line over here. And that represents that, our electrons can be moved about these 2 atoms like we just displayed here. And what's interesting to think about here is that this resonance hybrid structure, which is being represented here, is actually how this molecule is existing in real life. So in this second example, you can see that there's multiple resonance structures, not just one, and they can exist in each of their resonance states, but their resonance hybrid state is their least energy state, which means they are most stable and they want to exist sharing those electrons in this region. So they are not in a higher energy state. So back to this first example here, I can see that I have a negative charge on these outer oxygen atoms when I'm delocalizing my electrons. And so there's only one negative charge, not mixed formal charges, as you can see down in this second example. So it doesn't matter where I delocalize my electrons, I'm going to have a net dipole, net negative dipole within the whole molecule, no matter how I rearrange my electrons, which results in a full net negative charge on this resonance hybrid structure. So it just exists naturally or in real life with bearing a full negative charge on that molecule. So moving into our second example here, again, we are just trying to build our resonance structure and determine where we can break and form those bonds. So first I'm going to look at, again, like my double bond there on the bottom, or sorry, on the top oxygen atom connected to the nitrogen, the bottom molecule section down here. And my first initial thought is to bring my pi bond up. Again, I am breaking my pi bond and moving my electrons from this pi bond region into my electron pair, my lone pair region up on this side. So again, directionally you want to move it from the pi bond to the oxygen atom. And then I'm going to, again, delocalize atoms from my bottom oxygen charged atom down here and into forming a pi bond, which results in this second structure. So then I'm going to do the same thing on my second structure. Again, I'm thinking about the delocalization and also the moving of my formal charge. So since I delocalized my electrons and made 3 lone pairs up on my top oxygen atom, that made 7 valence electrons when we only want 6. So again, moving my negative charge up on that top oxygen atom, and now it's not bearing it on that bottom left hand side because we moved a set of lone pairs into a pi bond, changing its formal charge. And so I can see again here that I can delocalize some more. So I'm going to delocalize again this lone pair into a pi bond. And from this pi bond, I'm going to move it back to its lone pair, and which results in a different structure, and so which is this third structure here. We do not want to replicate and change any more moving of the electrons because it can just make recessive work, and it's not necessary if you're just continuously putting arrows where you've already moved your electrons. Showing it one time, it can understand and interpret that that's where they're going to be delocalized. So the minimal amount of arrows possible is better. And so now we can think about where exactly the delocalization of electrons occurred and build our resonance structure. So here I see that our delocalization happened on the outer sides, and that there's a net negative charge on the outer oxygen. So I know that I'm going to be bearing a negative charge the entirety of the time as this molecule is existing. And then a positive charge on that inner nitrogen atom. So I'm going to have that always be positive. And that is a little bit about how we draw resonance structures. Thank you.